Good evening, everyone.
Good evening, Professor.
Good evening, Professor.
Give me 2 minutes. I'll just set up.
Professor, one question is that the assignment solution will be shared to Professor with us.
Yeah. I will share it in a couple of days.
Okay, sure. Yeah. One of
Yeah.
the problem, the second problem, we didn't not sure about the answer actually. So
Yeah. I'll share it with you in a couple of days.
Okay. Thank you.
Yeah.
Sir, hello.
Yeah.
Sir, Arunachalam here, sir. Sir, actually, I am unable to upload the assignment through Google link.
You
So,
should upload through your Smail account only.
Yeah, I sent, sir. I sent already to your Smail account only. But
No. You should be able to upload it through Google form that they have given, no? Why weren't you able to upload?
Yeah, sir, that's a problem, sir. Already I told you, no, sir. By mistakenly, I uploaded my earlier other subject assignment. That's why
Okay.
That's why I sent through your mail ID, sir.
Okay. I will look into it. Yeah.
Okay, please consider, sir.
Yeah. All right. So can we get started? Okay.
Yes.
Yeah. So what we will do in today's class is try to understand the concept of invariants. So in order to drive that point, let me start from a vector. So for example, let us say this is your x-axis. And so let us say this is x1 axis, x2 axis. xy can also be written as x1, x2 axis. Okay. And now in that, I am representing a vector. This is the vector that I am talking about. Right? Let's call this vector v. Now, this vector v can be written as, if you say each grid point is 1 unit, what will be, how will you write this vector v?
2, 1.
2, 1.
2, 1. The projection onto x-axis is 2, projection onto y-axis is 1. Very good. So you have 2, 1 as your vector. So in other words, we can write this as 2 e1 hat plus 1 e2 hat, where this is the unit vector e1 hat and that is the unit vector e2 hat. So that is equal to e1 hat means 1, 0, e2 hat means 0, 1. That will be 2, 1. That is how you can write. So any vector in 2D, any vector v can be written as a linear combination of the basis vectors. So this e1 hat and e2 hat are called basis vectors. Is that clear?
Yes, sir.
Yeah. Okay. Now let us look at a scenario wherein, so I am expressing, so when I write v is equal to 2, 1, I am saying that the vector v is expressed with respect to a coordinate system x1, x2 frame. Right? With respect to that frame, I have expressed v is equal to 2, 1. Now let us imagine a scenario wherein I have chosen another coordinate system let us say this is x1 dash and perpendicular to that is x2 dash. So that means I have rotated my coordinate system by an angle theta. Instead of x1, x2, now I have my new coordinate system. The new coordinate system is with respect to x1 dash, x2 dash. So along the fact that I have written x1 dash, x2 dash, let me define new basis vectors along that new frame of reference. Let us say I am using blue color. This is E1 hat dash. This is my E2 hat. And this is my E2 hat dash. Right? Do you agree? I'm just saying that I have my new basis vectors. E1 hat dash is along x1 dash. E2 hat dash is along y2 dash, x2 dash. Now, if the same vector v written with respect to x1 dash, x2 dash frame, what should be the components? So the v can be written because now my basis vectors are, I can write as a linear combination of some value into E1 hat dash, some value into E2 hat dash. If you look at this vector v, that is projected along E1 hat dash. So that means the projection of v along E2 hat dash is 0. Along E1 hat dash, whatever is the length of the vector. What is that length of the vector? Square root of 2 square plus 1 square, that is root 5. So now my v can be written as root 5 E1 hat dash plus 0 E2 hat dash, or in other words, I can write root 5 0. Do you agree? So my vector v, now if I carefully observe my vector v, if at all it is written with respect to x1, x2 frame, is represented as 2 and 1. The same vector v, if it is represented with x1 dash, x2 dash frame, that should be written as root 5 and 0. In both the cases, the magnitude of this vector with respect to x1, x2 frame is root 5, right? Magnitude of this vector with respect to x1 dash, x2 dash is also root 5. Do you see that? So the point that I'm trying to make here is I am representing the same vector v. Depending on the choice of my coordinate system, the elements of the vector will change. If my choice of the coordinate system is x1 and x2, then my elements are 2 and 1. If my choice of the coordinate system is x1 dash, x2 dash, then my elements are root 5 and 0, depending on the choice of the coordinate system. However, so in these two frames of reference, this is one frame of reference, that is x1, x2 frame. This is x1 dash, x2 dash frame. In both the frames of reference, the elements of the vector have changed because the coordinate system is different. But there is something about this vector did not change. That is the magnitude. The magnitude of the vector remains the same. That means I would call the magnitude of the vector is invariant under coordinate transformation. What do I mean by that? I mean, the meaning of that is if I choose x1, x2 as my frame of reference, if I rotate rigidly that frame of reference to x1 dash and x2 dash, depending on the choice of my coordinate system, the values of the elements of the vector will change, but the magnitude of the vector remain the same, right? So then the magnitude of the vector is called invariant of these vectors. Is there any question there?
Sir, that new coordinates, I'm not able to grab it, sir. Why we are going with x1 dash minus x2 dash?
No, I have chosen another coordinate system which is going along x1 dash, x2 dash. If I choose a different coordinate system, depending on, because that is easier, so I have chosen that. Instead of that, I could have chosen something else. The point that I'm trying to make is, if it is x1, x2, you have these two numbers. If it is x1 dash, x2 dash, if they are chosen like that, then this is root 5, 0. If you have chosen some other coordinate system, for example, if you have chosen x1 double dash, x2 double dash, then again you will have a different value. So this will be my projection, right, onto x1 double dash, and that will be projection on the x2 double dash. Then it will be having a different set of numbers depending on this angle theta, isn't it? I could have chosen any coordinate system. Depending on the choice of my frame of reference, the elements of the vector will change. But in all the cases, the magnitude remains the same.
Understood.
Yeah. So since the magnitude does not change under coordinate transformation, that is what is called invariant of a vector quantity. Okay. Now, when we are talking about a tensor, a second order tensor like stress, we have discussed that stress is a second order tensor which will have component sigma 11, sigma 12, sigma 13. Because it is a symmetric tensor, sigma 121 will be also sigma 11, sigma 22, sigma 23, sigma 13 and 31 are same, sigma 23 and 32 are same, sigma 33. So whenever I have written this, this assumes a choice of a coordinate system. I would have chosen my coordinate system to be x1, x2, x3. With respect to this coordinate system, I have written the components, isn't it? Because the first index represents the normal to the surface and the second index represents the direction of the quantity, as we have seen in the previous class. You remember that? If you remember this picture, so now I have shown you in the previous class this is your x1 axis, that is your x2 axis, then that is your x3 axis. Then the traction vector on this surface, this component is sigma, the normal to the surface is x1 axis, and this quantity is in the direction of x1 axis. So this is sigma 11. This is the shear component, then this is sigma 12, 1 is normal, 2 is the direction in which it is. And this is sigma 13, right? So that means whenever I am writing these components of my tensor, I would have defined my x1, x2, x3 coordinate system. Is that clear?
Yes, sir.
Yeah. Now, like in the previous case, instead of choosing x1, x2, I have chosen x1 dash, x2 dash, x3 dash, some other coordinate system. If I have in a, this is say x1, x2, x3 frame of reference. Now let us say I have another frame of reference x1 dash, x2 dash, x3 dash frame of reference. Then also my tensor, second order tensor sigma will be sigma 1, 1 dash. Why am I saying dash? Because it will not be numerically equal to sigma 1, 1. Sigma 1, 1 dash, 1, 2 dash, 1, 3 dash, sigma 1, 2 dash, sigma 2, 2 dash, sigma 2, 3 dash, sigma 1, 3 dash, sigma 2, 3 dash, sigma 3, 3 dash. So the elements of this tensor will be different because the coordinate system is changed. But although the elements of the tensor have changed, there will be some invariants, meaning that do not change. Like the magnitude did not change for a vector, for a tensor there will be invariants. So if it is an nth order tensor, will give you n invariants. No, sorry. I would call not n invariants. If it is a 3 by 3 matrix, if it is represented, then you will have 3 invariants. So what are these 3 invariants? They are called I1, I2 and I3. These 3 are 3 invariants. Okay. So the I1 is your trace of the matrix sigma. That is sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3. What we are saying when we say invariant, the sum of these diagonal terms should not change, which means sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3 should be same. The trace should be same. That means whether you write with respect to this coordinate system or this coordinate system, the trace of these two matrices should be the same. That means this must be equal to sigma 1, 1 dash plus sigma 2, 2 dash plus sigma 3, 3 dash. Because the trace of this matrix is this, sum of these 3 elements, and trace of these things is sum of these 3 elements. That remains unchanged, and hence it is called sigma 1, 1 dash, sigma 2, 2 dash, sigma 3, 3 dash. Okay. I2 is called sum of the principal minors. What is a principal minor? You know what is a principal minor? So suppose if you take sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 1, 2, sigma 2, 2, sigma 2, 3, sigma 3, 1, 3 or 3, 1, sigma 2, 3, sigma 3. Principal minor means first you take this fellow. The minor of that will be you remove that row and that column, then sigma 2, 2, the determinant of the remaining matrix, sigma 2, 2, sigma 3, 3 minus sigma 2, 3 square. That is the first principal minor. Sum of that. Second principal minor means sigma 2, 2 you have to take. So that row and that column if you remove, sigma 1, 1, sigma 3, 3 minus sigma 1, 3 square plus sigma 3, 3 is the third principal. So sigma 1, 1, sigma 2, 2 minus sigma 1, 2 square. So this quantity remains unchanged. That is your I2. So even in this equation, just replace that with a dash, then it should remain unchanged. That is your I2, sum of the principal minors. I3 is determinant of C, det of sigma. You know how to calculate the determinant of this matrix, right? How do you calculate the determinant of this matrix? So sigma 1, 1 times sigma 2, 2, sigma 3, 3 minus sigma 2, 3 square minus sigma 1, 2 into sigma 1, 2, sigma 3, 3 minus sigma 1, 3, sigma 2, 3 plus sigma 1, 3 into sigma 1, 2, sigma 2, 3 minus sigma 1, 3, sigma 2, 2. That will be the determinant of that matrix. That will be invariant. So, for a second order tensor, for a 3 by 3 matrix, you have I1, I2, and I3. There are 3 invariants. They do not change. Either these 3 can be your invariants, or you can also have sigma 1, sigma 2, sigma 3, the principal stresses. Are also invariants. What is the meaning of that? Meaning whether you take this matrix or this matrix, you find the eigenvalues of this matrix and this matrix, they will remain the same. You will get the same eigenvalues. Only then this is a valid coordinate transformation. That is what we call that is why the eigenvalues. So we know the eigenvalues of stress tensor or principal stresses. Did we discuss that or not?
No, sir.
Sorry,
We did not discuss
Not yet, Professor.
No, no.
not yet. Okay. So you know what is the meaning of eigenvalue? Okay, let us look at this fellow. Okay. What do you mean by eigenvalue? Suppose if you have a matrix A, how will you find the eigenvalues of the matrix A? We have learned it in your high school.
A minus lambda I.
So we say that how to find eigenvalues of A. What you need is you should say determinant of A minus lambda I equal to 0. That will be an equation, and then use that equation and solve for lambdas. And lambdas are the eigenvalues. This is what we call characteristic equation. Right? Okay. So now why should we do this? If you have, how do you know that these are giving you eigenvalues? Before
That's
we do that, we should understand what is the meaning of an eigenvalue, physical meaning of an eigenvalue. Okay. Now let us look at this fellow. In the last class, did we talk about traction vector?
Yes.
Yes, sir.
So what is traction vector T? Traction vector can be written as stress tensor at a point and the normal to a plane that gives you traction vector on that plane, isn't it? The dot product of stress tensor and a normal vector to a plane will give you traction on
Traction
that
vector
plane,
on the plane.
traction vector. So now let me see this in a different perspective. Let us say A is a matrix like sigma, X is a vector like n. Then when I multiply a matrix A with a vector X, then what will I get? Some vector Y. Isn't it? Like what I got traction, similarly I get some vector Y. So now let us look at this particular scenario. What is the physical meaning of this? Let us try to get some geometric meaning to this. What this is telling me is the following. Geometrically, this is what it is telling me. You have a vector X. When this vector X is operated by matrix A, this matrix A, when it is operating on vector X, it is transforming that vector to another vector Y. Right? Some other vector, I don't know what this vector is, it will be generally it is transforming to some other vector Y. And that is what this statement tells you. Ax equal to Y means matrix A operating on a vector X to give me a new vector Y. It can be any new vector. All of you agree with that? Is this clear?
Yes, sir.
Yes, sir. Yes, Professor.
Yeah.
Sir, one question.
Yes, please.
Sir, initially you said that for a second order tensor, actually,
Mhm.
you will have, if you have a 3x3 matrix, then you have 3 invariants, right? Like,
Correct. Yes.
then why are we also getting a fourth, like a principal stresses are also invariant? That is like,
Because you will see that I1, I2, I3 can be written in terms of principal stresses and vice versa. Either these three or these three, because they don't change. Okay, I1, I2, I3 can be written in terms of principal stresses. So that is why I can say that sigma 1, sigma 2, sigma 3 are invariants. And then I can write I1, I2, I3 in terms of principal stresses. Okay?
okay, got it.
Yeah.
So does that mean both are same?
They are not the same. So it is like I1, we will see in a moment. Okay, please wait for some time. We will see in a moment. So now the idea that I am trying to say is that if you have an operator A is seen as an operator. A second order tensor by definition is something, a mathematical object, which when operates on a vector will give you another vector. A second order tensor or a matrix in our case, when it is operated on a vector, will give you another vector. Okay. Now, let us look at a special case of this. Let us say when you are doing AX, the resultant one is not is Y, but Y is lambda times X. What is the meaning of that? Lambda is a scalar. Meaning, when matrix A is operating on X, it is resulting in a new vector, but the new vector's direction is same as X, but the magnitude is different. Magnitude is multiplied by lambda. That means this vector, the matrix A is operating on vector X in such a way that the direction of the vector is not changed, but the vector is only either stretched or contracted. If lambda is greater than 1, then the X is stretched. Lambda is less than 1, then X is contracted. That means the magnitude of the vector alone is changing, but the direction of the vector is not changing. Right? So here in this special scenario, the direction of the vector X is retained, but the magnitude is changed. The resultant one will give a different magnitude, but the direction is remained the same. Direction was not changed. So in German language, eigen means self. So here you have a vector X, and vector X remained retaining its own direction, self direction, and hence X is called eigenvector of A. Eigenvector of A. And the lambda in this case, whatever the amount of stretch or contraction, lambda is called eigenvalue of A. Right? So whenever you have such a transformation, AX is equal to lambda X, then this problem is what we call eigenvalue problem. That means the orientation of the direction of the vector is not changing. It is only either getting stretched or contracted or remained the same, both magnitude. Lambda is equal to 1 means when the eigenvalue is 1, then the vector remained exactly the same. When the eigenvalue is less than 1, then the X is contracted. When the eigenvalue is greater than 1, then the X is extended. Okay. Is that clear? That is the meaning of an eigenvalue problem.
Why A is not mentioned as a tensor?
No, this is now I am talking about a linear algebra. I am assuming it to be a a linear operator, a matrix. Now, when it
Okay.
happens to be a tensor, tensor can be written as a matrix. Then the whatever is the object, then we will call that as an eigenvalue of that object. Suppose if A happens to be a stress tensor, a second order tensor, in this case, it's a linear operator. A is a linear operator. Okay, in a linear algebra sense. Similarly, a second order tensor is also a linear operator. So I am coming from linear algebra and then explain saying that, okay, now A happens to be a second order tensor, then X is a vector, then that will be a traction. If A is a stress tensor, then when it is operating on a vector N that is normal to the surface, then the resultant is a traction vector. Okay. In general, traction vector will not be in the same direction as N, right? In general, traction vector will be in some other direction than N. That is why it is very similar to Ax is equal to Y scenario or Y is equal to X scenario. Now, in a case where Ax equal to lambda X, then what happens? I am rewriting this equation. I can write Ax minus lambda X equal to 0. 0 null vector, not 0. This can also be written as Ax minus lambda times Ix. I is what? Identity matrix. Now I can write A minus lambda I times X equal to 0. 0 vector. Now, this is what my eigenvalue problem. Again, this is same as this problem, right? Eigenvalue problem. Now, the trivial solution for star is X is equal to null vector. If X is equal to 0, then equation will be satisfied or not. But that means that will for any that X is an eigenvector. So that means null vector is an eigenvector to any matrix. Because if you multiply any matrix with null vector, you will always get null vector. So null vector is an eigenvector to every matrix. So that is not a special scenario. That is a trivial solution. But this equation will also be true, the non-trivial solution. What is the non-trivial solution? That means the non-trivial solution, this equation will be true only when this matrix is singular, because the right hand side has to be 0 when this guy is singular. When will that be singular? What is the meaning of A minus lambda is being singular?
Determinant not equal to 0.
Yeah. No, singular is 0. Is singular, that implies determinant of A minus lambda I must be equal to 0. That is when the matrix A I minus lambda I will become singular. And that is the reason why whenever you are required to find the eigenvalues of a matrix A, you do A minus lambda I, determinant of A minus lambda I equal to 0. Somewhere we have written here. The reason for that is this. Okay. Now, determinant of A minus lambda I, if it is a 3 by 3 matrix, then lambda cube something will come. This equation will be, if it is a 3 by 3 matrix, A is a 3 by 3 matrix, then it will be an equation with lambda cube terms. Implies there are 3 roots to the equation. That means you will have lambda 1, lambda 2, lambda 3. These 3 are called eigenvalues of A. So corresponding to lambda 1, what we have said, Ax equal to lambda is a scalar x. But we don't have 1 lambda, but 3 lambdas. So corresponding to lambda 1, you will have x1. Ax2, corresponding to lambda 2, there will be another vector x2. Corresponding to lambda 3, there will be another vector x3. So the vector x1, x2 and x3 are the eigenvectors of A. So if you have a matrix a matrix A, it has 3 by 3 matrix. It has 3 eigenvalues, and corresponding to each eigenvalue there will be eigenvectors. So 3 corresponding eigenvectors. Okay. So let us look at one scenario. Suppose if A is 2 by 2, what happens? You will have 2 eigenvalues and 2 eigenvectors. Okay. Now we have seen that the traction vector is equal to sigma dot n. In general, the traction vector will be in some other direction. Why would I say that? Suppose if you look at this picture, the traction vector will be in some direction, because traction vector is equal to on n1 plane sigma 11, sigma 12, sigma 13. Right? It will not be in the direction, the n to this surface is 100, but this is definitely not in the direction of 100. Do you agree or not?
Yes, sir.
Yeah.
Yes, sir.
Now imagine what if sigma 12 is equal to 0 and sigma 13 is also equal to 0. Then traction will be sigma 11 0 0. Do you agree?
Yeah.
Then the traction on that vector is equal to sigma dot n. N is 100. Then what happens to the direction of the traction vector?
Aligns with the sigma 11.
Aligns with 100, n1, right? E1 hat aligns with E1 hat. So that means if on this plane the shear components are 0, that means sigma 12 and sigma 13, if they are 0, then you have only one normal component, right? What is such a plane called? You have a plane on which shear stresses are 0.
Principal plane.
That plane is called principal plane, and the normal stress in that direction is
Principal stress.
principal stress. So now you let us write this scenario. You said my T is equal to sigma dot n, and if you have a scenario you only have sigma 11 and here sigma 22 and there is sigma 3. That means there are no shear stresses here. On this plane there is no shear stress, on this plane there is no shear stress, on this plane there is no shear stress. Now if I take, so this stress state can be written as sigma 11 0 0 0 sigma 22 0 0 0 sigma 33. Right? This is what we call principal state of stress, because only normal stresses are there. If you take that sigma 11 0 0 0 sigma 22 0 0 0 sigma 33, if I find the dot product of that with 1 0 0, what do I get? Sigma 11 times 1 0 0. Do you agree or not? So this is A, x is equal to, this is lambda x. So this sigma 11 is my eigenvalue. This x remains the same, that is my eigenvector. So when, that is the reason why I call, so sigma 11, sigma 22, sigma 33, that is how you will get the principal stresses, right? So if I take my sigma sigma 11, sigma 22, sigma 3, sorry, sigma 12, sigma 13, sigma 12, sigma 13, sigma 22, sigma 23, sigma 23, sigma 33. If I find the eigenvalues of this guy, then they will be sigma 1, sigma 2, and sigma 3. They are the three eigenvalues. Corresponding to that, eigenvectors V1, V2, V3. These three eigenvalues are my principal stresses, as we have seen here. And the corresponding vectors will be principal vectors. That means the plane on which the normal stresses are non-zero and shear stresses are zero. Okay? So you can see T is equal to sigma dot n. If this T happens to be some lambda times n, it's in the same direction as this guy, then lambda is called eigenvalue of sigma, n is called eigenvector of sigma. Okay? Because the direction did not change. So these, if you have the point that here we need to keep in mind, if your original frame of reference is x1, x2, x3, and the new frame, another frame of reference is x1 dash, x2 dash, and x3 dash. Now let us say if you have represented your sigma 11, sigma 12, sigma 13, sigma 22, sigma 23, sigma 33. I am not writing because this is symmetric. I am just writing this. Similarly, the same stress tensor with respect to the new frame of reference, sigma 11 dash, sigma 12 dash, sigma 13 dash, sigma 22 dash, sigma 23 dash, sigma 33 dash. It is the same state of stress, but written with respect to different coordinate frame of reference. Then, if you find the eigenvalues of this fellow and eigenvalues of this fellow, they remain the same. So, sigma, sigma dash. So, the eigenvalues of sigma and sigma dash remain the same. Okay, that is why they are invariants. Any questions here? Any questions?
No, sir.
Okay. Now, let us look at, for the sake of simplicity, I am just using some stress tensor to.
Excuse me, sir.
Yes.
Sir, these eigenvalues has to be real values or
For
it can
because stress tensor is symmetric, in linear algebra, we can actually show that for a symmetric positive definite matrix, the eigenvalues will always be real numbers. One can show that. And since the stress tensor is symmetric, you will always have these eigenvalues as real numbers because you cannot have imaginary number as your principal stress, isn't it? Because stress tensor is symmetric, it will always be a real number.
Okay, sir. Thank you.
Okay. So let us look at the stress states. Let us say sigma 11 is 100, sigma 12 is 20, sigma 22 is 50. Now let us find the eigenvalues of this fellow. How do I find eigenvalues? Sigma minus determinant of sigma minus lambda I, that means 100 minus lambda, 20, 20, 50 minus lambda, determinant that must be equal to 0. That implies 100 minus lambda into 50 minus lambda minus 20 square is 400, that must be equal to 0. That implies 100 into 50 is 5000 minus 100 lambda minus 50 lambda is minus 150 lambda plus lambda square minus 400 is equal to 0. That implies lambda square minus 150 lambda plus 4600 is equal to 0. This is the equation. So then can you find the solution of this equation? Lambda is equal to minus b plus or minus square root of b square minus 4 into 4600 a into c is 1 by 2. Can you tell me the values?
One not seven and 42.98
107
and 42.98.
107 and 43 or 42.98. That means 107 is not exact. 106 point something then.
107.01, sir.
Yeah. So 107.02 40
42.98.
correct. These are your lambda. So this is my lambda 1, that is my lambda 2. So let us call them as 107 and 43. Is that okay?
Yes, sir.
So that means this is my sigma 1 and sigma 2. This is in the principal frame of reference. What do we mean by principal frame of reference? In that, if it is 2D system, if that is my principal axis, so let us say principal axis is x1 dash, x2 dash, then I only have in this direction, sigma 1 is 107, this is 43. There is no shear stress. That means in the principal frame of reference, this is 107, 0, 0, 43. That is my sigma. Right? There are no shear stresses. That is the principal frame of reference. The idea is, what is I by I1? What is I1?
T1 plus T, sorry, lambda 1 plus lambda 2.
Trace of sigma. So here it is 107 plus 43. That will be 150. For the original matrix, 100 plus 50. So it remained the same or not? It did not change. You see that? Although you write the stress tensor in this frame of reference with the principal stresses, that is remained one determinant I3. Let us see. What is the determinant? 107 into 43. How much?
Four
4326.
4601. And the previous one? 5000 minus 400.
4600.
Yeah, the spot 01 is because we have rounded off here. That is why it is 01 is coming. Otherwise, it would also be same. Right? If you have taken 107.28 and 42.98, 107.02 and 42.98, then it would have come exactly 4600. So similarly, I2, if you calculate, it will remain the same. So you have calculated eigenvalues, correct? Now, how do you get eigenvectors? What is the definition of my eigenvalue problem? Sigma x or n is equal to lambda times n. Lambda 1 times n1. That is the first one. So sigma is what? 100, 20, 20, 50. N1, I am calling it as N1, N2 is equal to lambda 1 is how much? 107, isn't it? N1, N2. Let us say 100 N1 plus 20 N2, 20 N1 plus 50 N2 is equal to 107 N1, 107 N2. Right? That means 20 N2 these are the two equations, no? 20 N2 minus 7 N1 equal to 0 and 20 N1 minus 57 N2 is equal to 0. Right? So, what do I get? Can I solve these two equations? So, minus 7 N1 plus 20 N2 is equal to 0. 20 N1 minus 57 N2 equal to 0. This is equal to into 20 into is equal to 7. That is 27s are how much? Minus 140 N1 plus 400 N2 is equal to 0. Plus 140 N1 minus 57 into 7. How much? 399. That is about 400 N2. You will not be able to solve. You will get 0 only. So, what you will get is 20 N2 is equal to 7 N1. That implies N2 is equal to 7 by 20 N1. That means I can say if N1 is equal to 1, N2 will be 7 by 20. That is your eigenvector. You can choose one number, then that will be. So, this is the eigenvector for sigma 1 is equal to 107. Similarly, 100, 20, 20, 50, N1, N2. Second one is what? 107. And the second eigenvector is 43. 43, N1, N2. Then again 100 N1 plus 20 N2 minus 43 N1 equal to 0. That implies 100 minus 43 is how much?
57.
Plus 20 N2 equal to 0. That implies N1 is equal to minus 20 by 57 N2. Or N2 is equal to minus 57 by 20 N1. So the new vector N is equal to N2 is equal to, if N1 is equal to 1, N2 is minus 57 by 20. Corresponding to sigma 2 is equal to 43. So corresponding to this vector, that is the eigenvector. So this is the orientation of the plane on which sigma 2 is equal to 43. That means the angle between our initial angles are E1 hat and E2 hat. This is one vector. This is another vector. 1 and 7 by 20. So that will be somewhere here. And 1 and minus x1 and y minus 4. So another one will be like this. The angle will be the angle between 1, 0 and this. Okay. So like that, you can calculate eigenvalues and eigenvectors, which will tell you the orientation of the principal stresses. So the point that here I am trying to make here is that if you have a second order tensor sigma, it will have sigma 1, sigma 2 and sigma 3 as invariants, or I1, I2, I3. Because the I1, I2, I3 can be represented in terms of sigma 1, sigma 2, sigma 3. Okay. Any questions here?
Sir, in this context, the eigenvectors will be perpendicular to each other, N1 and N2.
Yes. Eigenvectors will be perpendicular to each other. You can actually show that. Because if it is a symmetric matrix, the eigenvectors will be orthogonal to each other.
Okay.
Yeah. We are not getting into those details, but yeah, you can take that. So now let us look at this thing. You have a stress state in some random coordinate system. The stress state is given as sigma 11, sigma 12, sigma 13, sigma 12, sigma 22, sigma 23, sigma 13, sigma 23, sigma 33. What is the meaning of that? This is with respect to a coordinate system whose basis vectors are something like that. Okay, whose basis vectors are E1 hat, E2 hat, E3 hat. Then you have both normal and shear components. Now, if your basis vectors are say N1, N2 and N3, these are all principal directions, let us say. That means because we said the principal directions are orthogonal to each other, now I can choose my principal directions as my basis vectors. If I choose my principal values as principal directions as basis vectors, then I can write my stress tensor in that frame of reference. Can I do that or not? I can choose in this frame of reference or in this frame of reference. That is up to me, isn't it? If I choose my stress tensor to be written in this frame of reference, what will change? The numbers, elements in the tensor will change. What will be the elements? Because they are all principal directions, will you have shear stresses?
No, sir.
So I can right away write all the shear components to be 0. I will only have principal component, normal component, that is sigma 1, sigma 2, sigma 3. So if you look at these two guys, you can say that this is the same state of stress. This is represented with respect to this frame of reference, and this guy is represented with respect to that frame of reference. So because when we are writing in different frames of reference, the elements that go into the tensor will be different, but the invariants remain the same. That means I1 with respect to the first one will be what? Sigma 11 plus sigma 22 plus sigma 33. That should remain the same even for the second one. Is that clear?
Yes, sir.
Yeah. Now I2. Let me write I2. What is I2 now? Can you tell me I2 with respect to the first coordinate system? Sum of the principal minors. What is the first principal minor? First principal minor?
Sigma 11 into sigma 22.
Sigma 22 into sigma 33
sigma 33
minus
Not sigma
23.
11. See, first principal minor means you take this element and that row and that column you remove. The remaining matrices determinant is the first minor. So the first minor will be sigma 22, sigma 33 minus sigma 23 square. That is the first minor. Do you see that?
yes sir.
And the second minor will be plus, you take sigma 22, the second diagonal element, and then remove that row and column. Then you will have sigma 11, sigma 33 minus sigma
13 square
plus sigma 11, sigma 22 minus sigma 12 square. Because if you take this one, then sigma 11, sigma 22 minus sigma 12 square. That is for the first one. Second one, what will be the principal minor? Sigma 2, sigma 3 plus sigma 1, sigma 3 plus sigma 1, sigma 2. So these two should be equal, correct? Now what is I3? sigma 1 into sigma 2 sigma 3 minus sigma 2 square minus sigma 2 into sigma 1 sigma 3 minus sigma 1 square. No, not like that, sorry.
Sigma 1 2.
Minus sigma 1 into sigma 1 sigma 3
Minus sigma 1 3 sigma 2 3.
plus sigma 1 3
Sigma 1
into
3 into sigma 1 2 sigma 2 3
sigma 1 2
Sigma
sigma
1
minus sigma 1 3 sigma 2 2.
how about the last with respect to this fellow, the principal frame? What should be the value?
sigma 1 into sigma 2 into sigma 3.
That is your determinant, right? So if you have to compute the invariance, it's much easier to compute in the principal frame of reference because they have to remain the same, right? If you know the principal stresses, it's much easier to compute these invariants. Anyway, so these three are our invariants of your stress tensor. Okay? All right. Now, any questions here? Yeah, if there are no further questions, now let me ask you this simple question, okay? I will give you a stress state sigma. This is stress state sigma, which is given by in the principal frame of reference. I am writing the stress state in principal frame of reference. I can write in any frame of reference, but principal frame of reference is easier to deal with. So I am writing it in principal frame of reference. Okay, this is one stress state. I am writing another stress state. This is sigma 1. And the second stress state is now looking at these stress states, which one is more closer to yielding? The question is the following. Which one of the above stress states is close to yielding? Is the question clear? Is the question clear?
Yes, sir.
Yeah. What do you think?
So it has to be sigma 2.
So we think that sigma 2 is close to yielding, right? By looking at that. So let us examine this, whether this is true or not. That is what failure theories allow us to examine this in a very nice way. Okay. So in order to do that, so keep this question in mind, and then we will now discuss various failure theories, and then in the end we will try to come back and answer this question. Okay. So in the last class, when we have started talking about failure theories, when we are not talking about stress state, right? A stress state at a point can be written either in this frame of reference or this frame of reference. It is up to us to write in any frame of reference that we want, correct? Now, typically, the failure theories are expressed in principal frame of reference because you only have to deal with 3 numbers. Vis-a-vis 6 numbers. Instead of dealing with 6 numbers, you can only deal with 3 numbers because it is exactly the same state of stress. It is written in with a different coordinate frame of reference. And hence, usually the failure theories are written in terms of in principal stress space. There is no reason other than that it is much easier to deal with fewer numbers. Is that clear?
Yes.
Yeah.
Yes, sir.
Yeah. So now let me move on and then move on to the next set of slides. Yeah. So in the last class, we have talked about general form of failure theory, which is written as a function of sigma 1, sigma 2, sigma 3. The reason why we write it in terms of the principal stress space is because it is easier to deal with. We only have to deal with 3 numbers instead of 6 numbers. And the failure theory looks like function of sigma 1, sigma 2, sigma 3 must be equal to some constant value, some critical value. And that critical value could be yield strength if it is a ductile material, or ultimate tensile strength if it is a brittle material. Okay, that is what we are trying to reach out to. So there are various failure theories for ductile materials. Historically there are these first 3 failure theories. The maximum normal stress theory is one of the very old failure theories, which is also called Rankine theory. What it tells you is that whichever normal stress is maximum in the given state of stress, for example, if you look at this state of stress, sigma xx, sigma yy, sigma zz are maximum. Look at the maximum value of these 3, and if the maximum normal stress becomes equal to the yield strength of the material, that is when failure happens. That is what Rankine theory says. And the maximum normal strain theory says, which is also called Savana theory, what it says is, corresponding to this stress state, you can also write the strain tensor, epsilon xx, epsilon yy, epsilon zz, epsilon yx, epsilon zx, and so on. Now you look at the normal strain, look at the maximum normal strain, absolute value of normal strain, and if that maximum normal strain becomes equal to the strain at yielding for a uniaxial tension test. When you do the uniaxial tension test, for example, this is your uniaxial tension test, and this is your yield strength. Corresponding to that yield strength for that particular material, there is some strain, right? That is what we call yield strain. When the maximum strain becomes equal to yield strain of the material, the maximum normal strain becomes equal to yield strain of the material, that is when the failure happens. That is the condition for failure as far as maximum normal strain theory is concerned. Then came the total strain energy theory, because what the genesis for the total strain energy theory is that, see, when you are dealing with stress or strain, these are tensorial quantities. Then the question came, see, you have a tensorial quantity which there are 6 components of strength tensor. Why is that you are only looking at one component? Why are we not looking at other components? So you are having a vectorial or a tensorial quantity, and but then you are comparing it with only the yield strength of the material, which is a scalar. So then they thought, okay, instead of coming up with a tensorial quantity to be compared with a scalar, why not we come up with a scalar measure for the failure estimation? What they said was, okay, let us calculate energy, which is a scalar, which is total strain energy, which is basically nothing but area under, suppose let us say this is sigma y, and now you take the area under the stress strain curve up to the onset of yielding, then that is what we call total strain energy. When that strain energy This is what we call strain energy at yielding. That is our criterion. So if after you have the sigma xx, sigma yy, sigma xz and all these things and corresponding strains, you can find out the inner product of sigma and epsilon and then get a energy from the state of stress and strain. And if that energy becomes equal to strain energy at yielding, then the failure happens. That is what is called Hayek theory.
Is it all the components or maximum?
No, not maximum. So now what happens is, if you let me write down, I think I have to show you that. How does it work? Let me.
Sorry, by this time I should have known, but sorry.
No,
for
no
trivial.
problem. No problem. Yeah. So the strain, and suppose if you have a three-dimensional state of stress, so you have sigma. I can write it in the terms of principal stresses, no problem, right? Because we have just now shown that the stress state, right? And corresponding to these stresses, you have epsilon 1, epsilon 2, epsilon 3, the strains. Okay. Then the strain energy can be written as 1/2 integral sigma dot d epsilon, which will become sigma 1 epsilon 1 plus sigma 2 epsilon 2 plus sigma 3 epsilon 2. That is your total strain energy. Okay.
Thanks, sir.
If you have a full strain tensor, let us say sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, sigma 3 1, sigma 3 2, sigma 3 3. And corresponding to that, you have epsilon 1 1, epsilon 1 2, epsilon 1 3, epsilon 2 1, epsilon 2 2, epsilon 2 3, epsilon 3 1, epsilon 3 2, epsilon 3 3. Then you can actually calculate something called sigma ij, epsilon ij, which is nothing but sigma I from 1 to 3, sigma j from 1 to 3, sigma ij, epsilon ij. That is your total strain energy. Okay. Then this value, if you are doing uniaxial tension test, the uniaxial tension test will be like this. Let us say this is my yield strength of the material. And I am not interested in the flash deformation. This is epsilon y. The strain energy at yielding is 1/2 sigma y times epsilon y. Do you agree? Then the total strain energy theory tells you if U becomes equal to Uy, that is when failure happens. Is that clear?
Got it, sir.
This is what we call total strain energy theory or Hayek's theory. And Rankine theory, maximum normal stress theory tells me, or is also maximum principal stress theory. You have sigma 1, sigma 2, sigma 3, three principal stresses, right? If sigma 1 is greater than sigma 2 is greater than sigma 3, maximum normal stress theory tells you that if sigma 1 becomes equal to sigma y, yield strength of the material, that implies failure. Maximum, that is Rankine theory. Maximum normal strain theory, this is called Savana theory. What it tells me, if my principal strains are epsilon 1, epsilon 2, epsilon 3, then if epsilon 1 is greater than epsilon 2 is greater than epsilon 3, if epsilon 1 is equal to epsilon y, what is epsilon y? This guy. Then that implies failure. So if you remember, I said my general form of my failure theory, is function of sigma 1, sigma 2, sigma 3. I can always write it in terms of principal stresses is equal to sigma c. That is how my failure theory should look like. Now, if I look at maximum normal stress theory, because it is ductile material, the sigma y c will be sigma y. Okay. So sigma 1 is equal to sigma y is the maximum normal stress theory. Is that okay? And maximum normal strain theory, epsilon 1 is equal to epsilon y. I can always write epsilon y in terms of sigma y, isn't it, right? Sigma y is equal to E times epsilon y. So epsilon y is equal to sigma y by E. Can I do that? So I can write this is sigma y by E. So epsilon 1 is equal to sigma 1 by E minus mu by E into sigma 2 plus sigma 3. So epsilon 1 can be written as sigma 1 by E minus mu by E into sigma 2 plus sigma 3 is equal to sigma y by E. That implies sigma 1 minus mu times sigma 2 plus sigma 3 must be equal to sigma y. That is maximum normal strain theory tells me. So then in this case, that is f of sigma 1 comma sigma 2 comma sigma 3. In this case, that sigma 1 is my f of sigma 1 comma sigma 2 comma sigma 3. It only depends on sigma 1. Right. Similarly, if you take total strain energy theory, 1/2 sigma 1 sigma 2 plus sigma 2 sigma 3, sorry, 1/2 sigma 1 epsilon 1 plus sigma 2 epsilon 2 plus sigma 3 epsilon 3 is equal to sigma y 1/2 sigma y epsilon y. That is what we have written, no? Yeah, sigma y epsilon y. That is half of gets cancelled. That implies sigma 1. Epsilon 1 can be written as sigma 1 by E minus mu by E sigma 2 plus sigma 3. Right? That is sigma 1 plus sigma 2 into sigma 2 by E minus mu by E times sigma 1 plus sigma 3 plus sigma 3 by E, sigma 3 into epsilon 3 sigma 3 by E minus mu by E times sigma 1 plus sigma 2 is equal to sigma y. Epsilon y is what? Sigma y by E. So E gets cancelled on all the sides. Sigma 1 square minus mu times sigma 1 sigma 2 minus mu times sigma 1 sigma 3 plus sigma 2 square minus mu times sigma 1 sigma 2 minus mu times sigma 2 sigma 3 plus sigma 3 square minus mu times sigma 1 sigma 3 minus mu times sigma 2 sigma 3 is equal to sigma y square. That is equal to sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 2 times 2 nu times sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3. Because everything comes, that is equal to sigma y square. That is your distortion energy theory. So this one, that implies square root of sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 nu times sigma 1 sigma 2 sigma 3 plus sigma 3 sigma 1 is equal to sigma y. Then this is your f of sigma 1, sigma 2, sigma 3. This is my sigmas. This is the functional form for total strain energy theory. Is that clear? So each theory is just a different functional form for describing whether the failure is going to happen or not, based on certain hypothesis. So this is your total strain energy theory. Any questions here?
Sir, one small question here is
Yeah.
these three failure theories, they are
Hmm.
only applicable for linear behavior, right?
We are assuming, if you, I have told you certain assumptions in the very beginning, that the material is assumed to be homogeneous and isotropic and linear elastic.
Okay, okay,
Yeah.
got it. Yeah, got it.
If those assumptions are not there, then these things may change a little bit. For
Okay.
now, the assumptions are the following: homogeneous, isotropic, and linear elastic. The material is this type, and there are no cracks. And now we are talking about three theories that are typical for ductile materials. First three theories we have talked about, and there are two more theories that. So first theory is maximum normal stress theory or Rankine theory. Second theory is maximum normal strain theory or called Savana theory. Third one is total strain energy theory, which is Hike's theory. And in the beginning, we only have these theories. But the problem with these theories, see, this is a very good progress from the first two theories to third theory, because first two theories are dealing with a tensorial quantity, and that tensorial quantity is compared to a scalar. Yield strength is a scalar quantity, right? Uniaxial yield strength. So it is comparing a vector with a scalar is not a good idea. Similarly, then comparing a tensorial quantity with a scalar is not a good idea. Then they came up with Hike's theory is a leap forward in terms of thinking about failure theories. What they said is, okay, now I am comparing a tensorial quantity with a scalar, which is not a meaningful thing. So let us also generate or develop a scalar equivalent from this tensorial quantity. And that is how they generated this energy term. The moment you have generated the energy term, then energy is a scalar. That energy is compared to the energy at the yield strength of the material. That is how the total strain energy theory came in. However, although total strain energy theory is a leap ahead in terms of the thinking, all these three theories suffer from the fact that they do not match with the experimental data very well. The experimental data is not very well matched for these three theories. Then people came up with the new theories. The fourth theory is what we call distortion energy theory. Or it is also called von Mises-Henke theory. And the fifth one is maximum shear stress theory, which is also called Tresca theory, Tresca-Guest theory. These two theories are extremely popular for ductile materials. All these theories are ductile materials only we are talking about. They're very popular for ductile materials. And these two theories match excellent with the experimental data. And what is the reason for them matching excellently with experimental data and why they are more popular is something that we will see in tomorrow's class. Is that okay? Unless you have any further questions on today's class. Do you have any questions on today's class? Is everything clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. All right.
Yes, sir.
Yes, sir.
Thank you. See you tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Sir, what request?
Yes, sir.
Ramadan Yadav. Okay.